All right, today we're going to shrink down way, way down to explore a world that's all around us but is completely invisible. It's a world where the normal rules of physics kind of seem to bend and where everyday materials take on these incredible, almost magical new properties. So let's dive into the absolutely fascinating science of the small, nanotechnology.
You know, this whole idea really got its start way back in 1959, thanks to the brilliant physicist Richard Feynman. He gave this now legendary lecture where he just imagined a future where we could grab and move individual atoms and molecules. He basically said, hey, look, down at this tiny scale, there's a whole new frontier for science to explore. And wow, was he right?
So, just how small are we actually talking about here? Well, the key unit of measurement in this world is the nanometer. That is 1/billionth of a meter. And look, that's a scale that's pretty much impossible for our brains to even comprehend, so let's try to put it into perspective.
Okay, think about this. The double helix of your own DNA, that's about 2 nanometers wide. Now, compare that to a single strand of your hair, which is a colossal 60,000 nanometers thick. We're talking about building things on a scale of just a handful of atoms. It's wild.
So here's the plan for our tour of the nano world. We'll start with what I call the surface area secret. Then we'll look at the nano toolbox and figure out how we see the invisible. After that, we'll walk through a cool case study with golden rods, and we'll finish up by looking at nature's very own nanotech.
All right, let's tackle the first and, honestly, the most important idea. Why is the nanoscale so special? What's the big deal? Well, it all comes down to a really simple but incredibly powerful secret about surface area. Let's just ask the key question right here. What really happens when you take a chunk of some material, let's say a block of gold, and you just keep chopping it down into smaller and smaller and smaller pieces until you hit that nano level?
The answer? The surface-to-volume ratio goes completely haywire. Okay, picture a sugar cube. It has 6 sides, right? Now smash it with a hammer into powder. You still have the same amount of sugar, the volume hasn't changed, but you've just created thousands and thousands of new surfaces. At the nanoscale, this effect is taken to the absolute extreme. A huge percentage of the material's atoms are now sitting right on the surface, totally exposed and ready to react with the world. And that changes, well, everything. And this is the perfect example of the consequences. Bulk gold, like in a ring, is that familiar yellow color, and it melts at over 1,000 degrees Celsius. But gold nanoparticles can show up as red, or blue, or even purple depending on their size, and they melt at a much, much lower temperature. It's the exact same gold, it just has a totally different surface-to-volume ratio. Mind-blowing, right?
Okay, so we know why the nanoscale is so interesting. But how do scientists actually build things that are this tiny? Let's open up the nano toolbox and take a look.
It really boils down to 2 main philosophies. The first one is called top-down. Think of it like being a sculptor. You start with a big block of material and you just carve away everything you don't want. The other approach is bottom-up, which is more like building with Legos. You start with the individual atoms and molecules, and you assemble them piece by piece into the exact structure you want.
A classic top-down method is something called ball milling. And honestly, it's basically a high-tech grinder. You throw your material into a container with these tiny, super hard balls, you spin it around, and the collisions just pulverize the material down into an extremely fine nanopowder. Super simple, but hey, it's really effective. Another top-down technique is sputtering. The best way to think about this one is like a microscopic sandblaster. You bombard a target material with these high-energy particles, which literally knocks tiny bits of it loose. These bits then fly off and coat another surface, creating an ultra-thin film.
Now for a bottom-up approach. One of my favorites, chemical vapor deposition, or CVD. With this, you inject a special gas into a hot vacuum chamber. The heat breaks down the gas, and its atoms settle down onto a surface, building up a brand new layer, literally one atom at a time. It's like you're painting with gas. So we can make all these amazing nanomaterials, but that leads to a pretty big, obvious problem. If they're so ridiculously small, how on earth do we even see them to know what we've actually made? And that is the absolute crucial point. Nanoparticles are often smaller than a single wavelength of visible light. What that means is a traditional light microscope is completely useless. The light waves just pass right over them without even noticing they're there. It's like trying to feel a single grain of sand with a giant beach ball. Just not gonna happen. So to see them, we use electrons instead of light. And there are 2 main types of electron microscopes,
A scanning electron microscope, or SEM, scans the surface of an object to give you this beautiful 3D image of what it looks like on top. A transmission electron microscope, or TEM, on the other hand, shoots electrons through a super thin slice of your sample, giving you a 2D image of its internal structure. So one looks at the outside, the other looks at the inside.
Okay, now let's see how all this stuff actually comes together in the real world. We're going to put these concepts, making things and seeing things, into practice with a really cool case study, growing gold nanorods.
So scientists use this really clever bottom-up recipe called the seed-mediated approach. First, they create these teeny tiny seed nanoparticles of gold. Then they pop these seeds into a growth solution and add other chemicals that encourage the seeds to grow, but, and this is the key part, only in one direction. This forms these perfect little rods. The most important thing here is that by tuning the chemicals, you can precisely control the final product.
Now, check this out, because this is where it gets really interesting. In the experiment, scientists just varied the amount of one simple thing, hydrochloric acid, or HCl. Now look at the optical behavior. In sample A, with low or no acid, you get one result, but then you add a moderate amount in sample B and bam! The peak of light it absorbs shifts dramatically. Then add way too much, like in sample D, and the behavior completely changes again.
And here it is. Here's the why, revealed by the SEM. At low acid, the nanorods are just kind of scattered around, separate from each other. But at that perfect, moderate concentration, they self-assemble into these dense, beautifully aligned structures. This ordered packing, this is what caused that massive shift in color we just saw. But then, at the highest concentration, it all goes wrong, and they just clump together in a disordered mess.
So what's the physics here? Well, the nanorods are coated with a chemical that makes them naturally repel each other. The chloride ions from the HCl weaken that repulsion just enough, allowing the rods to get a little bit closer and line up in that nice, orderly way. But if you add too much acid, you kill the repulsion completely, and they just smash together randomly. The acid is acting like a tuning knob for self-assembly.
As absolutely amazing as all this is, it's really important to remember that humans, we didn't invent nanotechnology. We're just students, learning the rules from the original and still undefeated innovator, nature itself.
I mean, just think about the stunning iridescent colors on a butterfly's wing. Guess what? There's no blue or green pigment in there at all. That color comes from nanoscale structures on the wing that perfectly manipulate light waves. Or think about a lotus leaf. Its surface is covered in these nano-sized bumps that make it super repellent to water. A drop of water just beads up and rolls right off, taking all the dirt with it. It's a self-cleaning surface designed by nature.
From medicine and electronics to energy and new materials, nanotechnology is already changing our world. This ability to design and build matter right from the atom up gives us a level of control that's just unprecedented. And it leaves us with this huge, tantalizing question. Now that we can truly build with atoms, what problems are we going to solve next?